Good morning,
So in
sir.
the, yeah, good morning. So in the previous class, we have been discussing on a few concepts of first order system, where we have seen that you have inverse Laplace transform and all you have taken, and you got the function C of t is equal to 1 minus so 1 minus e to the power of minus at. So this is that function what you got. C of t is equal to 1 minus e to the power of minus 80. So with the help of this function, 1 minus e to the power of minus 80, we are going to draw the graph for that. So this is the graph where it shows the response of the system. So you can see that we have given some percentage here like 0.63, 0.9 and 1 etc. So 63%, 60%, 90%, 10% and 100%. So that is what you can see, and you can see that the system performs in this form. So it gradually goes to the steady state response. So where we have two things, that is time constant, t we have tr and rise time, fall time, time constant, everything can be found. So stable state, you can see that it is at this particular point. So we are going to see, we have the major general function for this, that is c of t is equal to 1 minus e to the power of minus 80. So by using this function c of t is 1 minus e to the power of minus 80, we are going to do it further. So what is time constant? So we will, all of you have drawn this diagram, no, in the previous class?
Yes, sir.
Okay. So we will continue from here. So time constant, we can say that the time constant is the time taken by the step response to rise to 63% of the final value. So what you can see here is, you can see we start from zero. So we are starting from zero, and slowly it rises further, and it goes like this and then comes to the stable state. So this is what you can see here, this position, this point where it comes to 63% of the final value. Final value is how much? 1. So when you are coming to the 63% of the final value, you call this as the time constant. So you have the time constant is the time taken by the step response to rise to 63% of its final value. So C of what is the equation we have studied? C of t is equal to 1 minus e to the power of minus 80. We are going to use this equation. So this equation you need to remember. So this is the equation C of t 1 minus e to the power of minus 80. So we are going to see that first one, we are going to see the three responses we'll be seeing. So the first one is the time constant, where you can see the system rises to 63 percentage of the final value. Means if your final value is 1, you're going to be 0.63. So that position, that time, it is called as the this time is called as the time response. So this is what we are going to see. You can just note down the time constant is the time taken by the step response to rise to 63% of its final value. This is important. So we have taken the same equation, C of t is equal to 1 minus e to the power of minus 80. So t greater than or equal to 0. So we have to see here. So we have 0, 1 by a, 2 by a, 3 by a, 4 by a, etc. So at t is equal to 1 by a, we'll take at t is equal to 1 by a, substitute t as 1 by a. In place of t here, we have to substitute 1 by a. So let us substitute t is equal to 1 by a. So a and a gets cancelled, and you get e to the power of minus 1. So you can just write the values for c of t, 1 minus e to the power of minus 1. So you'll be getting 0.63. So C of t you'll be getting 0.63. So this graph, all of you should draw it. Last class, if you have not drawn, you draw it straight away. From this graph, you will be studying all the three transient response. So, so this is for the first order system. So we have been studying the first order system, unit step response of first order system. Usually they used to ask these things for your examinations. So explain the first order system of the unit step response of first order system. So we have to explain this equation. So C of t is equal to 1 minus e to the power of minus at, and then we have to proceed further with this graph. So you can see in the graph as well. So all of you have to draw this graph properly, and you can see that you have different points. You will be defining the time constant and transient response in this graph. So first one is the time constant is what we have seen. We have seen that when the response rises to 63% of the final value, you call this as the time constant. So for that we use the same equation, and C of t is equal to 1 minus e to the power of minus at. We substituted t is equal to 1 by a. We got 0.63. So you may be thinking, why 0.63? So we have got this from the value here by calculating C of t. So from here we are saying that when the system reaches 0.63% of the final value, you call this as the time constant by using the equation. Okay. So C of t is 1 minus e to the power of minus 1, and you get it as 0.63. Also, e to the power of minus at, you get e to the power of minus at as 0.37. So that as well you can see. So the reciprocal of the time constant 1 by a, and is the exponential frequency. So these are some of the things with respect to time constant. Then we will move on to the next one, that is called as the rise time, and it is denoted as TR. So rise time is a little more ahead, like we have to see the entire system reaching till this point we have seen, and now we are going to see that the entire system reaching to almost 90%. So this is very important. So that is what we call it as. First one is called as a time constant, and the second one is called as the rise time. So rise time is denoted as TR. So you can see here we have mentioned it as TR, and this is the time taken for the system to reach 90%. Okay, so the time for the, so you can just note down the first one, and then we will move on to the second. So complete it, time constant. So once you complete the time constant, we'll move on to the rise time. So you have completed that?
Yes, sir.
Okay. So we'll move on further with the rise time. So as I have told you, rise time is denoted as TR. And what does TR all talks about is that you can see that the system has to reach to the 90% of the value of maximum value. So maximum value is 1. So you have to reach 0.9. So the time for the uniform time for the wave, this is rise time. TR is the notation for that. The time for the waveform to rise from its 10% of its value to 90% of its final value. So it has to reach to its 90% of the final value from 10% of the value. Then we call it as TR. So you can see that it is clearly drawn in the diagram. So from here till the 90% peak. So from here to here, this point to 90% till here. So how much time it takes for the system to reach that point is called as the rise time. So you can just write down the definition for that. The time for the waveform to rise from its 10% of the value to 90% of the final. So it is given as Ct is equal to 1 minus e to the power of minus at, the same equation we are using here, t greater than or equal to 0. So now what we are going to see here, we have to find out the t, t1 and t2, because 10% to 90%. So what I have substituted here is, in place of c of t, I made it as c of t1 and c of t2. So t1 I will substitute as 0.1, and the same equation 1 minus e to the power of minus a t1, and next is t2 is equal to 0.9, 1 minus e to the power of minus a t2. So from these two equations we can find out t1 and t2. So the time between t1 and t2 is called as the rise time, and it is denoted as tr. So we can just take the logarithm of that and try it out. So we can see that TR can be written as T2 minus T1. So it will be 2.2 by A divided by A. And when you take the all those things logarithm and all, this side it is mentioned here, you can just note down this portion. So it is 0.1 is equal to minus e to the power of minus 8t2. So you will get logarithm of zero point 0.1 to the base e is minus 8t2, and t2 can be written as 2.3 by a. How this t2 has come? Okay, how this t2 has come? Same way, if you do, you will get t1 as well. So you'll get t1 and t2 both, and you can simplify this. When you get T1 and T2, it is just TR is T2 minus T1. So T2 is 2.3 by A minus 0.1 by A. So you'll get 2.2 by A. So this is what it is called as rise time. So all of you note down these things. So we have studied two concepts here. One is called as the time constant, another is called as the rise time. So the time constant, you got Ct as 0.63, and T for the value of T as 1 by A. And here you have found out Tr, you got Tr value as 2.2 divided by A. So in any problems, if they ask you to find out rise time, you have to find out Tr. So Tr can be found by using 2.2 by A. So in the figure also it is very much clear for you, from 10% to 90%. The other one is till 63%. Time constant is till 0.63 or 63%, and the rise time is till 0 to 10 to 90%. So all of you completed. So all of you have completed?
Yes, sir.
Okay. So we got rise time as well as time constant. Now we'll see TS. So what is TS is from 0 to maximum. So you are going to see that when it reaches the stable state. Okay. So we'll see that. So here you have to see when this is somewhere around 2 percentage we can say. 2 percentage we can say. So that is what the difference is all about. So that's what we are going to see here when it reaches to the stable state. So settling time is called as TS. So TS is that the time for the step response to reach and stay within 2 percentage of the final value. So you are going to see that somewhere around 98%. Okay. So the time for the step response to reach to the stable state. Okay. Almost it is going to be in the stable state. So the time for the step response to reach and stay within 2% of the final value. If you see the figure, as I have told you, it will be within this place, that is this portion you can see. It is almost in the 2% range. Okay, so that position is very important for us to understand these things. So that point where the time for the step response reaches and stay, it need to stay within that 2% of the final value. If it is 1 is the final value, so within 0.98 and 1 it should be there. Within that 2% the signal has to be available. Then the system can be called, means we can say that it is settling down, or you can say that it is called as a settling time. It is denoted as TS. The notation is TS. So let us use the equation, the same equation. C of t is equal to 1 minus e to the power of minus at, and you get t greater than or equal to 0. So when you substitute all these things like 0 point c of t will be 0.98, 1 minus e to the power of minus at. Instead of t we have written ts. So let us take 0.0 is equal to, here is how this has come. So you on these things in your notebook. So you'll get logarithm when you take log of 0.02 is equal to minus 8 ts, and ts will be 4 divided by a. So c of t is equal to 0.98, 1 minus e to the power of minus 8 ts, and when you simplify it further you get t of s is equal to 4 by a. Simplification is there here. You have to take the equation c of t is equal to 1 minus e to the power of minus 8t. Substituting c of t as 0.98 is equal to 1 minus e to the power of minus 8t. Yes, we have written because of settling time ts we wrote. So let us do it with logarithm. So it is minus 0.02 is equal to e to the power of minus 8ts, and log, when you take log of 0.02 is equal to minus 8ts, is 4 by 8. So here the setting time can be calculated using the equation. So Ts is equal to 4 by 8. So you'll get the settling time. So 3 time constants you got. So all of you note down the settling time as well. So the equation what you get here is Ts is equal to 4 by 8. So all of you have completed that. So all
Yes, sir.
the three, yeah, okay. So all the three time constants you have written. So we are going to go further with a problem. Find the step response C of t for the system described by g of s is equal to 4 by s plus 4. Also find the time constant, rise time and settling time. So write down this problem. So we have studied all this equation for T of S is 4 by A and all. We have to use these equations further. So the first one question you can write down, find the step response C of T for the system described by G of S is given for you 4 by S plus 4, and also find the time constant, rise time and settling time. See, you need to know the very basic equations of Laplace and inverse Laplace. I am saying you again, so those equations are going to be used further. So in this module we need Laplace transform and inverse Laplace transform basic equations, whatever you studied in mathematics before. So if you are not remembering, just go through the book and understand those very basic equations of Laplace and inverse Laplace transform. So here g of s is given for us. It is 4 by s plus 4. We are asked to find out the time constant, rise time and settling time. So how to do these things is, we need to write the function c of s is equal to g of s into r of s. That is, you know that we have studied this equation before. The transfer function c of s by r of s is equal to g of s. So the same equation we can use here. C of s is equal to g of s into r of s. G of s is given for you 4 by s plus 4. So and r of s, you have to see the question properly. It is clearly told that it is a step response. So when it is a step response, you can substitute it as 1 by s. So I have substituted here as 1 by s. So I get 4 by s plus 4 into 1 by s. So write down, if you don't know, means you can just write down, since it is step response. Okay, since it is step response. So if they make it some other response, you have to change according to that. So let us move further. So this 4 by s plus 4 into 1 by s can be rewritten in this form. All of you try to write in this form. It can be written. Once we have written this in the previous uh, equation as well. So it 1 by s into 4 by s plus 4 can be written as 1 by s minus 1 by s plus 4. So if these two are the same, it is modified and written in this form. Once you write it, let me see that how many of you know to take the inverse Laplace transform for this function. Try taking the inverse Laplace transform. Take the inverse Laplace transform.
One minus e power minus 8.
Okay, 1 minus
E power minus 4t, sir. Sorry.
one c of t, you'll get it as 1 minus e to the power of minus 4t. So all of you should write down those inverse Laplace, at least 10 equations of Laplace and inverse Laplace. You need these things for this module 3. So one of you can just put it in the group, this Laplace and inverse Laplace from the textbook or somewhere, so that others can also note down in the uh, book. Okay, it's there in your mathematics textbook. Please go through those basic equations. So it is if you know, still you just go through it because one semester back you have studied. So C of t, you will get it as 1 minus e to the power of minus 4t is what you are going to get. So this is the equation what you got. So here, what you should understand here, what is the actual equation? C of t is equal to 1 minus e to the power of minus 8t. So here it is 1 minus e to the power of minus 4t. So what is a here? A is 4. So that is what you should understand and then simplify further. So first thing is what? Time constant. What is the equation for time constant t? It is 1 by a. So t is equal to 1 by a. A is 4. If you want, you can just note down these steps there. Write down. After this step, you can write down C of t is equal to 1 minus e to the power of minus 8t. So from comparing both the equations, we get a is equal to 4. So once you get a is equal to 4, you find out time constant t. T is, we have studied that t is equal to 1 by a. So it is 1 by 4, it is 0.25 seconds. What is the next one? Rise time.
2.2 by A.
Yeah, 2.2 by A. What is the answer?
0.55.
Yeah, 0.55. So 2.2 by 8. So it is 2.2 by 4. It is 0.55 seconds. What is the next one?
4 by A, sir.
Settling time.
Yes, sir, second.
4 by A.
1 second, sir.
So you'll get the next one, settling time. That is 4 by A. So you'll get it as 1 second. So all of you complete this problem. All of you note down this problem. So all of you have completed.
Yes,
So this
sir.
is what we have. This is what we have studied for first order system, and here we have seen the time constant, rise time, and settling time. So we got the time constant as 1 by a, rise time as 2.2 by a, and settling time as 4 by a. And you know that time constant is the time for the system to reach 0.63 second, 0.63 of the maximum value. Rise time is from 10% to 90% of the maximum value, and settling time is the time where the system is within the 2% of the maximum value. So these are the three things which we have studied with respect to the first order system, and we have also seen that C of t is 1 minus e to the power of minus 8t. So using all these equations we have done, and one of the problem where g of s is given for us, then seeing that it is a step response, we have used as 1 by s, and you need to see this step to this step is very important. Don't make any mistake. You have to put it in this form. You have to put it in this form, then only you can use the inverse Laplace transform. So you have to make this form of equation to be written in this form, 1 by s minus 1 by s plus 4. So once you do this, then you can use the Laplace, inverse Laplace, and you get C of t is 1 minus e to the power of minus 4t, where you have compared with the actual equation of 1 minus e to the power of minus 8t, and you say that a is equal to 4, and you use all these equations to simplify it further. So it's very simple question to do with. Once you just go through the equations, it will be easy for you. So once you complete this, we are going to go with little bit of theory concepts here, and then we will move on to the derivations for second order system. So all of you completed that. So we'll move on to the next topic, formal representation of second order system. So we are in module 3. So module 3 second topic, that is formal representation of second order system. So second order system representation can be given in this form: d square c by dt square plus a into dc by dt plus bc of t is equal to b of r, b r of t. So it is the general representation for second order system. So these things you have come across in your many other subjects as well. That when you have a second order system, you are going to have the representation in this form: d square c by dt square plus a dc by dt plus b c of t is equal to b r of t, where a and b are the real constants. So here we are going to see more about the here we are going to see more about the theory concepts, and then we will move on to little bit of derivation for second order system and proceed further. So some of the things we will discuss here. So all of you can just note down the formal representation of second order system. See this before we studied the three time responses. That is very important. You mark it as important: time constants, rise time, and settling time. That figure and all those things. So first order system. So that is important. Usually it's they ask this question: explain the first order system for a unit step response. So you have to write all this: time constant, rise time, settling time, everything. Now we are going to see the second order system. So in the second order system, we have seen the general representation of a second order system, or the formal representation of a second order system, and it is given by this equation. So A and B are the real constants. Now let us see some of the terminologies or terms which is required for us further. So first one is natural frequency. Everyone is quite familiar with that. Natural frequency is denoted as omega n, and the frequency of oscillation of the system without damping is called as a natural frequency. So it is the definition for that: omega n, the frequency of oscillation of the system without damping. So next we have damping ratio. It is called as zeta. So zeta is the damping ratio is so you can just first note down the natural frequency definition. The frequency of oscillation of the system without damping is called as the natural frequency, denoted as omega n, and damping ratio is zeta. So you might have seen this symbol representation. So it is zeta is represented in this form. So you have to take like this, and so like this. This is the notation for zeta. So it is called as zeta, ZETA. So damping ratio we can define as: damping ratio is a dimensionless measure describing how the oscillation of the system decay. So after a disturbance, so once the disturbance is there, how the system decay for the particular oscillations, whatever it takes place, and it is denoted by the letter zeta. So that notation I have shown you. And we have three conditions here when and can be vary from underdamped. You have underdamped, undamped, underdamped, critically damped, overdamped, and also we have all four conditions here. So zeta is called as the damping ratio, and this damping ratio, when zeta is equal to 0, we call it as undamped, and when zeta is less than 1, we call it as underdamped, and when zeta is equal to 1, you call it as critically damped, and when zeta is greater than 1, you call it as overdamped. So it is a damping ratio, and it's a dimensionless measure describing how the oscillation of the system decay after a disturbance. So if you make some disturbance for the system, how it decay back. So that is what, and we have four classifications for this. We can call undamped, underdamped, critically damped, and overdamped based on the value of zeta. So zeta is equal to 0 is undamped, zeta less than 1 is underdamped, equal to 1 is critical damped, and greater than 1 is called as overdamped. The equation for zeta, or you call it as the damping ratio, it is exponential decay frequency divided by natural frequency, which is in radians per second. So you can note down these things for damping ratio. This is all theory concepts. We can understand it. So all of you can just note down this damping ratio. So write the notation properly. So in some textbooks, they might have used a different notation. So when you are reading other textbooks and all, don't get confused with these notations. So one, you can go with the prescribed books, what is there in the syllabus. So zeta is exponential decay frequency by natural frequency in radians per second. You have completed that?
Yes, sir.
Okay, so let us go back to the equation 1 here. This is the equation 1. So if you just try to take the transform for that, so let us see, taking the Laplace transform for that equation 1. So how you can write the Laplace transform for that equation 1, d square c by dt square plus a into b dc by dt plus bc of t is equal to b r of t. Let us see that when you take the Laplace transform for that, you can write it as s square c of s plus a s c of s plus b c of s plus b r of s is what the Laplace transform for this equation. So take the Laplace transform for that equation 1. So you'll get s square c of s plus a s c of s plus b c of s plus b r of s. So this is very important for a second order system, that you should remember is equation number 2. So this equation 2 you should remember, because this equation is very important for a second order system. So C of s by R of s, you call this C of s by R of s as the transfer function. So C of s by R of s, if you take it to one side, or you take it this side, so the left terms will be b divided by s square plus as plus b. So this is very important to understand this denominator, that is called as the characteristic equation, and you write it as s square plus as plus b is equal to 0. So that is called as the characteristic equation, and you have s square plus as plus b is equal to 0. So this characteristic equation is the denominator for this. So this is equation number 2. C of s by R of s is b by s square plus as plus b, and you call this as the characteristic equation. So further on, I may ask you that what is the characteristic equation for the second order system. So all these things you should remember. So when a is equal to 0, the system is said to be undamped. So remember these things. When a is equal to 0, the system is said to be undamped, and the poles of the transfer function C of s by R of s would be on the j omega axis of the s-plane and would be purely imaginary. So this is what one of the condition you can say when a is equal to 0. If you take a is equal to 0, the poles of the transfer function would be on the j omega axis. We have seen zeros and poles in the starting. So the poles will be in the j omega axis of the S-plane and will be purely imaginary. These are some theory things what you have to understand. When a is equal to 0, it will be an undamped condition. So we have the equation for C of s by R of s as b by s square plus as plus b. This is for the second order system, and you give it as equation number 2, and from that you can write the characteristic equation as s square plus as plus b is equal to 0. For one of the condition when a is equal to 0, you can say it is an undamped condition, and your poles will lie on the j omega axis and will be purely imaginary. So you note down these things. So you may get in the question paper that explain damping ratio, explain natural frequency. So all those things can be asked. What is the formal representation? So theory questions can be asked from this section. So you have to understand all these things. So complete it. So you have completed.
Yes, sir.
Yes, sir. Okay. So you can note down these things. So if all of you have completed, we'll move further. So this is the continuation of that. So the natural frequency omega n is the frequency of, we have already seen the natural frequency omega n is the frequency of oscillation of the system. The poles of this a is equal to 0, the system, this already we have just discussed now. When a is equal to 0, the poles will be on the j omega axis at plus or minus j root b. We have omega n will be root of b, and b will be written as the same thing. B will be written as omega n square. So what you're going to get here is b is equal to omega n square for a is equal to 0. So if the complex poles of the transfer function C of s by R of s lie in the left half of S plane, the system is said to be underdamped. So this is next condition called as underdamped. So if the complex poles of the transfer function lie in the left half of S plane. So I just want to make you clear these things. We have studied these things before. Just once We'll just see those things. So this is the S plane, what we are discussing now. This is the j omega axis. So if the poles are lying on the j omega axis, you can see here, this was an example which was drawn for you in the last class. So the poles were lying on the j omega axis. So here you can see the poles lying on the j omega axis. So that is what we have seen in this condition as well. So this is what they are discussing here. If the complex poles on the transfer function lie on the left half of S plane, means this side. This is the left half of S plane. This much only, okay? This pole. This is the left half of S plane. So this is what we have been discussing now. If the complex poles of the transfer function lie in the left half of S plane, the system is said to be underdamped, and the complex poles have real parts. Sigma will be minus 1 by A. The magnitude of the value is the exponential decay frequency. So you can just note down these things. We will continue from here in the next class. From zeta, using this equation, zeta is equal to a by 2 omega n. We will start from there in the next class. You can note down this theory concepts. So I will stop it here for the day, and we'll continue it for the second order system in the next class further. You can complete these things. You can note down these things, whatever we have discussed today's class, and from this equation onwards, we'll be discussing further. Okay, you can complete it. Okay, then thank you.
Thank you, sir.
Thank you, sir.
Yeah, thank you. Thank you.